Good afternoon, and thank you for your patience. We'll start now. I'm Arun Serafin, Executive Director of the Emerging Technologies Institute at the National Defense Industrial Association. I'm very excited for today's webinar, Defense Energetic Materials 101, with Dr. Marcus Jones, who I'll introduce in just a moment. As modern warfare evolves, advancements in energetics, material science, and manufacturing are transforming how the U.S. and the world designs, develops, and produces munitions. Just as breakthroughs in microelectronics reshape computing, emerging energetic materials are poised to reshape the future of defense capabilities and the entire munitions industrial base. We're talking about things like alternatives to legacy propellants and explosives that have been used for decades, as well as entirely new materials that can increase range, lethality, precision, and survivability in ways previously not thought possible. Some administrative remarks before we get started on the webinar. One, all attendee lines are muted. Second, if you have a question during the webinar, use the question box, not the chat feature in the Zoom tool. We will try to do our best to get to them. You can ask questions whenever during the presentation, but we'll be focusing on questions at the end of the presentation. We're recording today's webinar for members who are unable to attend, and this webinar is just one of our continually monthly series that you can track on our weekly newsletter and find on our YouTube channel. Now it's my pleasure to introduce our guest speaker, Dr. Marcus Jones. Dr. Jones is a senior fellow at the Energetics Technology Center, or ETC. He was the principal author of the ETC study called Energetics and Lethality, the imperative to reshape the U.S. military kill chain, which highlighted how outdated energetic materials constrain U.S. weapons performance, and it called for a revitalized enterprise to restore lethality at scale. Dr. Jones received his PhD from Yale University in 2005. Dr. Jones, thank you for joining us, and I'm going to hand over the presentation to you.
Thanks very much, Arun. And good afternoon to all of you, and thank you for joining me for this NDIA Tech 101 session on defense energetic materials. I'm going to share my screen here in a way, hopefully, that allows you to see it. One moment. I think I have to start the show. Okay. If I could get some kind of acknowledgement that that is as it should be.
We don't see your screen yet.
You don't see my screen. Do you see my screen now?
Yep, we see your screen and it's your PowerPoint screen there.
Correct. How's that?
Yep, now I think you got to share your other monitor.
I don't have two monitors set up.
Oh, okay. Yeah, then you're good. We can see it. You're good.
This doesn't make any sense. Sorry. You do or you don't? Do you see the notes and everything else?
Yes, we see the notes and everything else.
I don't understand why that's happening. Okay. Try it this way. How about now? Can you still see my screen?
Yes, sir. We can see. That's it. You got it. You're good.
Great. And it's full screen.
It's full screen.
Excellent. All right. Well, like I said, thank you for joining me for this NDIA Tech 101 session. As Arun said, I'm Marcus Jones of ETC, known otherwise as the Energetics Technology Center. We are 501c3, located just outside the gates of the Navy's Arsenal at Indian Head, Maryland. And we serve as a kind of central source of technical and policy expertise for the U.S. defense community. ETC integrates a lot of deep competencies in energetic material science, in AI and machine learning applications, for energetics and chemical manufacturing into the full spectrum of defense acquisition analysis and support. My goal in the next 40 minutes is to explain in plain but hopefully precise terms what energetic materials are, why they matter to the Department of Defense, what's being done to advance them, and why everybody here, whether we're from government or industry, need to care about this topic. Energetic materials, as Arun said, are the chemical foundations of modern military power. They are the materials that make weapons move, that make them strike and destroy, and they couldn't be more important for how well or inadequately the U.S. military is able to fulfill its missions. So I'm going to work through this issue today in 4 parts. I'll start with a short technology explainer so everyone shares the same basic baseline. I'll ask you, please, to bear with me through it. I'm neither a scientist nor an engineer, so everything you hear will be an example of a person kind of having grabbed a scientific tiger by the tail and struggling to hold on to it. After a dive into the technology, I'll try to explain why even small changes in energetic materials have important implications for tactical and operational outcomes. And I'll try to get at what we mean when we talk about energetic materials in relation to lethality and logistics, which are 2 of the most important considerations for U.S. military effectiveness right now. And then at the very end, I'll describe some of the current efforts to revitalize the sector and open the floor for some questions. I hope you'll bear with me while I take a quick historical detour, because doing so reminds us that this business has always been about courage and chemistry together. In 1943, Allied chemists developed Torpex, a mixture of RDX, which was at the time a fairly new material, TNT, and aluminum powder. Torpex packed about 50% more energy than TNT, and underwater it was transformative. All of that extra aluminum had the effect of extending the shock pulse and doubling the destructive range of the material against submarine hulls. So when our submarines and torpedo bombers switched to Torpex, suddenly enemy ships that might have limped away from a TNT hit were breaking apart. And that wasn't luck. It was a conscious decision to take technical risk for tactical gain, to field something new because the payoff was worth it. It's the same acquisition mindset we need right now. We have materials that can arguably do for modern munitions what Torpex did for World War II, but only if we're willing to move fast, to test hard, and to accept managed risk. The chemistry has always been there. What's changed is our tolerance for risk. And that's exactly what the new acquisition reforms underway, I think, are trying to restore. So, what are energetic materials? Energetic materials, quite simply, are a practical military category: explosives, propellants, and pyrotechnics. Explosives deliver a shock wave useful for things like warheads and shaped charges. Propellants produce a sustained high temperature gas to accelerate something, to accelerate some mass, a missile, an artillery shell. You can think in this context even of a bullet. Pyrotechnics and initiators generate heat, light or smoke or gas for decoys or illumination or to ignite something else. Because different physics govern these different processes, as we'll see, detonation versus combustion versus controlled pyrotechnic reactions, this means that the use of energetic materials in any system involves different design trades and different testing approaches. So building up then, in the very simplest terms, energetic materials are the often invisible enablers of reach and effect. They determine how far a weapon can travel. They determine how fast it can move. They determine how much destructive energy it can deliver. Beyond that, as I'll stress later, they also, very importantly, shape the logistics of a military organization, by which I mean how many munitions a given platform can carry, how safely munitions and systems can be stored and handled, how reliably they can be produced at the necessary scale, and how quickly and at what price point, critically. If nothing else you hear matters today, I would have you remember primarily this. Energetic materials are quite literally that space, that core concern where physics and chemistry meet tactical and operational potential. To put it as simply as possible, they are the part of the weapon that actually does the physical work. If you accept, as I continually teach, that the core justification of military force, not the only justification for military forces, but the most basic and distinctive justification for military forces, is the application of lethal violence to create specific effects that achieve objectives on behalf of interests, then energetic materials still account for about 99% of the effect U.S. military forces are able to bring to bear on a practical challenge. They're compact, they're easy to overlook, but they're decisive. And understanding them gives you the clearest sense of what the real limits and possibilities of military power are. So before we dive deeper into chemistry and performance, I think it's worth grounding ourselves quickly in who actually does this work in the United States. Because it's not one lab or company, it's not one part of the government, it's an entire ecosystem that stretches from discovery to production. On the left here, you have discovery, places like Naval Warfare Center at China Lake, California, the Air Force Research Labs, the Office of Naval Research, working with universities such as Purdue or Texas Tech or what have you. This is where the molecules are invented. It's where the chemistries are modeled, and the first milligrams of a given material may be synthesized there. Next in the stage of the ecosystem comes development, the engineering side, which is led by facilities like the Navy's Indian Head Complex or the Army's Picatinny Arsenal, where those lab ideas are formulated into real propellants and explosives and warhead fills. The next step in the process, qualification, is where most good ideas start to slow down, or in the past few decades, good ideas go to die. Here, the materials are tested for things like sensitivity, stability, compatibility, safety under operational test and evaluation oversight. All of these processes are very rigorous. They're often multi-year efforts, but they're absolutely essential to achieve a material that meets the requirements and the needs of the military. At the final stage of this, very generalized ecosystem chain here, we reach production, which consists generally of a kind of a mix of government-owned plants like Holston and Radford, often run by prime contractors like BAE Systems or Aerojet Rocketdyne, part of L3Harris now, or specialty firms such as Lacamas Labs in Oregon that provide critical feedstock chemicals to the process. Each of these stages has its own risks. Each stage in this process has its own timescales. And crucially, for acquisition reform today, each stage has its own authorities. And the real challenge, as I'll try to emphasize later, is not just in the chemistry, but in connecting these different stages. That's where these new acquisition reforms announced by the Secretary are designed to fix, to make this pipeline faster, to align it better, and to make it more predictable in important ways. So let's start with the basics, the most basic, at least in terms of my understanding of it. The single most important physical distinction or characteristic for energetic materials is whether they deflagrate or detonate. Deflagration is ordinary combustion that travels by heat and mass transfer at subsonic speeds. The chemistry of the material produces hot gas over a period of time to do work, which is exactly what you want inside of a rocket motor or a gun chamber, for example. Detonation is fundamentally different. In that case, the reaction front is tied to a shock wave traveling faster than sound. That creates an almost instantaneous jump in pressure and temperature. That's the classic explosive event when you need a very high peak pressure quickly or a penetrating shock. So choosing the weapon's mechanical effect essentially consists in choosing the right chemistries, both in terms of delivering it to the target and affecting the target once it arrives. The challenge is playing these chemistries out in weapon systems practically. There are a lot of different items here on this slide, a lot of information. For that, I apologize. What you see here are a handful of the basic parameters that engineers use to compare materials. For explosives, we look first at something called detonation velocity and peak pressure, because those drive the shock and the brisance. Put more plainly, we want to measure an explosive's detonation velocity, or how fast the shock moves, and its peak pressure, how hard that shock hits. Because a faster, higher pressure detonation produces a stronger, sharper shock wave. That's the brisance. That's what actually does the cutting, the smashing, the fragmentation that determine how much damage an explosive will cause. For propellants, the most important metric is specific impulse. That's the key performance number that we look at. Specific impulse is the thrust produced per unit mass of a propellant. It's a measure, in other words, of how efficiently the fuel converts chemical energy into push. Specific impulse is the key number because it directly determines how far or how fast a vehicle can go for a given amount of propellant. And thus, it determines range, payload capacity, and how effectively a munition can perform its mission. I want to emphasize something I'll emphasize many times throughout the remainder of this talk. Performance on its own is not enough. I'm going to come back to that over and over again. Other factors also matter: energy density, sensitivity, thermal stability, whether a material can be manufactured at scale and at cost and reasonably quickly. All of these other factors, as we'll see, also determine whether a promising chemistry becomes an operational munition. These and other metrics are what let scientists and engineers, testers, and program offices translate lab chemistry into real-world capability and risk downstream in the acquisition process. So, when you weigh those considerations, my guess is that many of you are going to recognize immediately and already that you almost never field a pure lab compound. Designers build formulations that blend high energy molecules with binders and additives so the munition is safe to handle, that it's manufacturable, scale, and it meets mechanical requirements. Pure molecules like RDX, HMX, or CL20 bring performance, but they also impose sensitivity and supply challenges. A polymer-based explosive, for example, PBXs, wrap energetic crystals in a polymer matrix to dampen their sensitivity and provide mechanical strength. That's really important for you to understand what are called insensitive munitions, which probably seems to some of you like a bit of the misnomer it seemed to me when I first heard the term. Insensitive munitions deliberately trade off some of their peak power for improvements in safety and logistics. While the U.S. was fighting insurgents for 20 years in what we call asymmetric conflicts in which our opponents were in no position to challenge our firepower dominance, insensitivity was very nearly the overriding priority of munitions development and manufacturing. To put it mildly, that circumstance has changed for reasons many of you probably know as well as I do, and we'll talk about in a little bit. But to return just briefly to the information on the slide, for propellants, the oxidizer, the binder, and any metal fuel additives, plus the geometry of the grain, as it turns out, determine whether the burn, so to speak, of a solid rocket motor has a given profile, whether it achieves the necessary ISP for the munition to do its job. Those formulation choices are the engineer's primary lever to convert chemistry into usable capability according to requirements. So as I mentioned, but I'd like to stress here, having a higher energy molecule on paper is pretty meaningless unless you can actually make it reliably and put it into a weapon safely. Small changes in purity or in crystal shape can make a compound a lot more sensitive or stop it from mixing with the binder you need. Most ways of making these materials lean on just a few precursor suppliers, so the supply chains that support our defense energetic production base are pretty fragile. They're pretty vulnerable to disruption in an emergency. The military's program offices, those federal personnel responsible for taking taxpayer money and turning it into military capability, program offices are naturally quite conservative. If you want to swap out a source or a step in the process, you're probably going to trigger a very expensive process of retesting materials and components. And that pushes those program offices, I think very reasonably, back all the time toward old, proven materials that don't incur those kinds of expensive processes and costs. I should add here that what works in a bench lab sometimes falls apart when you try to scale it up. That's what's called pilot plant engineering. A pilot plant is the small scale production style facility where chemists and engineers take a lab recipe and they figure out how to make the material reliably, how to make it safely, and repeatably at something approaching real manufacturing scale. Pilot plant engineering, I've learned, is pretty messy and nonlinear, and it's where many interesting new prospects, again, stall. But to put it coldly, material control, supplier diversity, slow qualification rules, and all the headaches associated with scaling things up usually decide whether a promising chemistry can become an operational munition. Now, I've alluded to this important truism already, but I want to emphasize it again. Every step forward in energetic performance comes with consequences, engineering consequences. You always pay somewhere, usually in safety procedures, in production complexity, or in the need to redesign your manufacturing, or even the actual munition system. For program managers, all of these trade-offs represent real time and money. New chemistries require new plant hardware. They can require environmental controls. A higher density explosive may mean reworking fuses or the casing of the weapons or the software to achieve the intended effect. The ultimate point here is that you can't judge a weapon by one shiny number. What matters is how all the components interact to work together. A good example, a shaped charge isn't just how powerful the explosive in the warhead is. It's about the dance between the explosive and the metal liner that forms the jet. If you change the liner or the timing, the whole effect changes. And with insensitive munition designs, engineers will often give up some of the power just so the munition can better survive little bumps, survive heat, rough handling in the real world. Again, it's the overall system that really matters, importantly for that. So let's turn to how energetic materials do the things we care about in defense terms. This is, again, an admittedly somewhat busy slide, but I often overestimate just how much information to include in cases like this. I'll start with a loaded sentence. Range is not a linear function of propellant quality. It's exponential through the rocket equation. Konstantin Tchaikovsky's rocket equation, 1903, amounts to saying that a rocket's speed gain depends on how efficiently it burns fuel and how much of its total mass is propellant.
And because that relationship is exponential, even small improvements in fuel efficiency or energy density make a big difference in range. That means a comparatively modest percentage improvement in ISP or energy density compounds over the flight and becomes a noticeably larger percentage increase in range for the same vehicle and payload. So in concrete terms, that translates into real operational changes. It means that you can attack from farther away. You can cover the same target set with fewer launch platforms, or you can keep loitering systems on station for longer periods of time, which opens conceivably a wider targeting space. The same point holds for gun systems and rockets. More energy or better impulse changes the muzzle energy and thus the effective range and lethality for a given projectile mass. And all of this, by the way, changes logistics because you need less propellant mass per mission to achieve the same effect. Or you can carry more payload or a bigger warhead instead. What we're talking about here is lethality. The important thing is not to think of lethality, which is a much abused and overused term these days. The important thing is not to think of it as a property of a chemical. It's the system output. It's how the chemical energy becomes mechanical work on a target. So lethality isn't just the chemical alone. It's not the energetic material by itself. It's the real world damage you get when that chemical's energy is turned into mechanical work by the entire weapon. Blast, fragments, the jets, the timing, the geometry. So the practical measure is the effect you can deliver per kilogram, because that's what drives warhead size. It's what drives how many warheads you can carry. It's what drives the mission and logistics consequences. For blast fragmentation weapons, brisance and peak pressure determine fragment speed and blast impulse. So a higher brisance explosive will often increase the radius of incapacitation against soft targets. For shape charges, a shape charge is an explosive device designed so that when it detonates, the blast energy is focused into a narrow, kind of high-speed jet, like a single fast-moving slug that can punch through armor or other hard targets. For shape charges, small changes in explosive performance or liner geometry can produce really big changes in jet velocity and penetration depth. The clearest metric for military planners and the program managers who supply them with their munitions is effect per delivered kilogram. A higher effect per delivered kilogram lets you shrink warheads or carry more warheads for the same payload mass. That allows you to alter platform design, logistics, mission planning, all the stuff I was talking about. That's the basic point to reiterate. Chemistry matters, but only insofar as it's married to engineering and system design. So all of this is to talk around the basic point I'm trying to make, that energetic improvements ripple through platform design. If you can get the same effect from a lighter warhead, that improved effect can buy sensors, it can buy improved guidance, therefore, it can buy extra fuel for the entire munition, or it can simply buy more rounds per sortie. All of these are force multipliers in operational terms. Designers constantly trade payload for range. Better energetics move that curve in your favor. They can enable longer reach or larger payloads without changing the platform. Operationally, that means safer launch positions and reduced exposure to enemy fires. And as you might expect, higher energies also yield faster, more maneuverable weapons, which make them harder to intercept and a heck of a lot more problematic a target set for the enemy to deal with and defend against. Those system-level benefits are why we continually emphasize that small material gains you achieve through the use of different energetic materials can have big effects on force posture and survivability. So these performance gains I've been talking about don't mean very much unless you can get the munitions where and when you need them. Higher energy density shrinks the mass, shrinks the volume needed to achieve a given effect. That enables you to ease your strategic lift. It enables more on-platform loadouts, greater number of munitions per aircraft, or perhaps per VLS cell. But if the energetic ages poorly, you pay for that in a higher number of inspections down the road, rotations, a higher life cycle cost because the munition has to be replaced at an earlier point. All of that reduces readiness. All of that constitutes those engineering trade-offs we talked about earlier. Likewise, a higher degree of sensitivity in the energetic material forces stricter handling conditions, and it means you might have to harden your storage facilities, and that constrains movement and raises expense. Also, and the importance of this is not to be overlooked, if the chemistry depends on a single source, precursor, or a very fragile manufacturing process, the capability can evaporate during conflict. A militarily meaningful improvement must survive the whole logistics chain. That means production, transport, storage, and distribution. But none of these performance attributes, I think, can be considered independent of acquisition concerns. That's what I'm really driving at with this, with the kinds of issues many listening to this webinar are going to care about most. Even when an energetic material shows a lot of technical promise, the real challenge is timing and cost. If you dig into any of these issues, you'll frequently see the terms qualification and certification. These terms refer to the formal, often very slow testing and approval steps that demonstrate a material and the way you make it to ensure that it meets the military's needs in terms of performance or safety or regulatory rules. All of these have to be addressed before a material can actually be placed in service. Qualification and certification are slow by design. They're very important for safety. They also have the effect of keeping potentially transformational chemistries in the lab for years, maybe forever. So qualification and certification, major hurdles that slow any prospect of improving energetic materials and defense systems. Then, assuming that qualification and certification can be achieved, when manufacturing scale-up begins, new problems emerge. Producers have to deal with impurities, with heat management, with solvent recovery. All of these take money and they take engineering depth and time to deal with. And because new energetics may need entirely new plant layouts, they may need new environmental controls, they may need new waste systems, that capital footprint itself becomes a major barrier. The core question for defense acquisition we faced regarding energetic materials for the past several years has been, can we shorten that calendar without compromising safety? Can we shorten that calendar in such a way that superior materials reach the field before they're obsolete? Is there some measure of risk we can define and deal with intelligently without giving up the potential advantages of these technologies? So while qualification and scale up, chew up time and money, I think it's important to remember that even tiny gains, as I indicated, tiny gains you can realize in performance, a few percent better propellant, say, they act like compound interest across hundreds of missiles when you factor those gains into entire munitions inventories. And that's exactly how marginal wins stack into real operational overmatch. Operational overmatch is a key term here that I would have you bear in mind. You can think of overmatch as compound interest for warfighting. A 3% gain in ISP in a solid rocket motor may look tiny in the lab, but when you apply it across hundreds of missiles, it becomes a big change in reach or the number of targets you could conceivably cover. A helpful anecdote to keep in mind along these lines, imagine a little naval fleet operating somewhere in the littorals, maybe in the South China Sea someplace, in waters not far from the coast. That little fleet is given the ability to push its anti-ship cruise missiles 10% farther because their propellant was improved by just a few percent. That increase allows all of the elements of that fleet to stand off a little farther, perhaps from a contested choke point, stand off a little farther from an area that's heavily covered by enemy munitions. That has the effect of reducing the risk that fleet faces to its ships and allows commanders to execute missions more safely, possibly just as effectively from a greater range. It's not one spectacular miracle. It's the accumulation of those tactical, those marginal wins that change the game in operational and strategic terms. Small advantages are magnified when they become common. So you think of one prototype missile with amazing range versus a whole fleet of them where every missile is just a little better. I think it's fair to say that commanders will almost always value the latter because it changes doctrine and day-to-day planning. In a long fight, cutting 10% off each round's weight adds up fast. You either make fewer supply trips, you carry more firepower with the same logistics. You can think of this as sustaining operations for weeks longer simply because each round weighs a little less and needs less special handling. I found that concrete examples along these lines help. Modest ISP gain in cruise motor might turn a local strike capability into an over-the-horizon strike capability. Suddenly, a shore battery that looked safe at a certain number of nautical miles becomes vulnerable. A high energy per kilogram explosive might let an attack helicopter carry 2 equally effective anti-armor rounds instead of 1. That's a meaningful change in sortie effectiveness. A less sensitive formulation can be the difference between requiring a special segregated magazine for a munition or special handling considerations and being able to co-locate munitions with other supplies, which has the effect of speeding up theater buildup and logistics and reducing the footprint of a logistics convoy. These are the kinds of everyday tactical advantages that aggregate into strategic overmatch. Consider this here, this image as a set of concentric coverage rings. If you look closely, each colored loop shows how far a particular class of Chinese missile can reach from its launch points. Imagine nudging those rings outward by a few percent. That's what a small, fieldable improvement in propellant or energetic materials does. A 10% bump in range turns in a 2,900 kilometer ring into about a 3,100, 3,200 kilometer ring. It can turn an 850 kilometer anti-ship range into a roughly 930 kilometer anti-ship range. Those extra hundreds of kilometers suddenly change which ports, which choke points, which patrol lanes are inside or outside the reach of a munition system. Practically, that means an American fleet that formerly had to operate near the inner rings could conceivably stand farther off. That reduces its exposure to coastal defenses. A target that seemed safe at a certain distance can now be held at risk. Areas that required escorts or special logistics, they become easier to supply or force protect. Again, when you multiply that shift across hundreds of missiles and many patrols, then that operational picture emerges. Fewer platforms are needed to cover the same target set. Convoys carry more effect per shipment. Commanders get new options for doctrine and maneuver. A map like this, I think, hopefully makes concrete how small, repeated improvements in propulsion and in energetics push those range rings outward, and by compounding across the force, produce the kind of overmatch we care about. Okay, let me dwell for a little bit now on some of the policy-related issues associated with this. If you remember one thing about the situation of the U.S. defense energetic ecosystem relative to that of our competitors, let it be this. For about 2 decades after the Cold War, the United States largely stopped pushing the energy content of our propellants and explosives. We doubled down on big advantages we had at the time in precision munitions, in both capabilities and numbers, which really was quite striking an advantage in the 80s and 90s. That advantage in precision munitions. And we doubled down on safety, which mattered a heck of a lot. But in so doing, our acquisition processes also got very cautious and siloed. Over the past few years, a handful of key studies have called this out very clearly, not least an important study from ETC. All of these studies emphasized how we underinvested, we let processes calcify, and we came to treat energetic materials like kind of brown package commodities rather than true design variables for range and lethality. That's an important consideration for the current U.S. operational and strategic predicament in the most important scenarios, especially those involving potential conflict in the Western Pacific. We are likely to be outranged and outmassed. Meanwhile, the evidence is that the Chinese especially kept chipping away at the chemistry and the manufacturing of energetic materials. On top of that, you have to consider the actual precarious state of key supply chains. We have lots of single or sole source suppliers, foreign dependencies, some real environmental and qualification hurdles. When you add all of that up, you can well understand the sense of alarm that arose among key members of Congress and in parts of the Department of Defense. The good news is that the Congress and the DoD have started to move. There is a national energetics plan. The 2024 National Defense Authorization Act established a new Joint Energetics Transition Office in the Industrial Base Policy Office in the Defense Department, which actually just became operational this year. There is a push to actually demonstrate possibly the most important new energetic material, CL20, in real systems, and not in the long term, but in the immediate future. All of this is about putting energy release back into the trade space of design and engineering and manufacturing, and responsibly so, I hope, so our weapons fly farther and hit harder again. The public conversation about advanced defense technology often centers on electronics and sensors and autonomy and stuff like that, but the energetic core of most of those munition systems hasn't changed very much in more than half a century. And again, this is the part that delivers the physical effects I've been talking about. The majority of U.S. munitions today still rely on formulations developed long before the Vietnam War, things like TNT and RDX and HMX. The principal reason why they're used so extensively is because they remain dependable and they're dependably straightforward to produce. But their performance limits are well known, and our competitors are working to move beyond them. Over the past 20 years, China and Russia have both fielded newer, more powerful energetic compounds in some of their key systems. That has had the effect of giving their munitions, in some cases, greater range, higher velocity, and increased lethality per unit weight. That's a very subtle, but in important cases, a decisive kind of overmatch. When a missile can fly farther on the same booster mass, or when a shaped charge can penetrate more deeply with the same volume of explosive, those gains accumulate into advantages that alter outcomes. As those studies I mentioned have shown, the U.S. Defense Energetics Enterprise, and by enterprise I mean that whole network of laboratories and production plants and suppliers that sustain these substances, it's scientifically quite mature and quite capable, but it is industrially fragile. Many key chemicals are produced at a single domestic site, or they're imported from foreign sources. Just as importantly, the defense acquisition process has until recently proven incapable of bringing any of them out of the lab and into our weapon systems. Those testing and qualifications processes take years and decades, and the specialized workforce that understands these materials throughout the entire developmental chain is shrinking pretty fast. This slide here is a few years old. I think it's about 3 years old, but there's no real reason to think the trend has changed. What it shows is the scale and intensity of China's investment in energetics research. If you look at the rankings, the top 5 institutions publishing in this field are all Chinese. The Beijing Institute of Technology alone has more papers than all the US national labs combined. Over roughly about a 7 or so year period, Chinese scientists published about 7 times as many papers in this field as their American counterparts. And that's not, just an academic curiosity. It reflects a deliberate national strategy. The Chinese military directly funds and supports its top universities and research institutes to work on energetics and train the next generation of chemists and engineers. You can see the results in their systems. Their missile ranges, their payloads, their overall performance has been steadily improving for more than 2 decades. So while the data here are a snapshot from around 2021, 2022, the trajectory is pretty clear. They've built a large, coordinated, well-resourced enterprise focused on exactly the technologies that determine reach and payload and overmatch. A good example, I think, of what that concentrated, well-resourced kind of effort would look like in practice is CL20, which is one of those chemistry stories that sounds like science fiction until you think about what it might actually do for a warhead or rocket. CL20 was first made and characterized at the Navy's China Lake Research Facility by a scientist named Arne Nielsen in the late 1980s, hence its designation as CL20. It was a 20th compound developed at the China Lake Research Facility. And soon after it was developed, it immediately turned heads because on paper, it packs more energy per gram than old favorites like RDX or HMX. It has a better oxygen balance and higher crystal density, which translate into higher detonation pressure or more impulse for a given mass. In fact, it's considered the most powerful non-nuclear explosive the U.S. Ever discovered. From the 1990s onwards, labs in the US and in Europe and in Asia ran tests to see whether it could replace or perhaps augment existing ingredients and propellants and warheads. It was explored as a gun propellant, a solid rocket motor ingredient, and a more powerful explosive filler. But the story after that, those lab phases, is where reality set in. It can be more sensitive, it's harder to process, and moving from a promising laboratory material or a bench sample into a safe, repeatably manufacturable material suitable for weapon systems requires really big investments in pilot plants, and handling infrastructure, qualification testing. For that reason, despite its likely performance upside, CL20 is never quite swept into broad use in US systems. It's remained a kind of tightly managed niche technology while developers have wrestled with its sensitivity and cost and problems associated with scaling it up. The evidence suggests that the Chinese military produces it at something like industrial scale and has built it into some of their systems. So it's an important part, I think, of that global energetics landscape we're mindful of. But the practical lesson is simple. A great molecule is only half the story. Congress has ordered the DoD, fortunately, to run real demonstrations so that we can perhaps stop debating CL20 on paper and measure the gains it gives us in range and effect and talk about cost in real terms. Okay, I've tried to talk about what advanced chemistry can deliver, higher energy, smaller form factors, longer reach. The next question is how quickly the system can adapt to exploit those gains. And that's a story not of chemistry, but of policy. None of it matters if we can't get materials through the system and into weapons that warfighters can actually use. And that's where the real news is happening, I think. Over the last few weeks alone, the department has launched some of the most consequential acquisition reforms in decades, all aimed, to my way of thinking, at fielding capability faster along the lines I've described. So before I close, I want to take just a minute to talk about what those changes could mean for the future of energetics. The reforms in this case are explicitly trying to make acquisition act like a warfighting function. Speed over process, accountable leaders, and most importantly, perhaps for folks on the call, investable signals for industry. I see that as important for energetic materials in three specific ways. First, prototypes and demonstrations should get prioritized. I think the documents that have been released on this acquisition reform make pretty clear that the warfighting acquisition system, as it's being called, will field technology faster and accept more risk to get capability into warfighters' hands. Practically, that means smaller, mission-focused demonstrations of a new explosive or propellant, something like CL20 or a new binder formulation or something like that. Those demonstrations may be able to proceed under sort of tailored pathways rather than full decades-long qualification. That shortens the lab to shot time. We pair test plans to operational key problems. Second, I think the department is trying to give the market better demand signals. Bigger, longer buys, especially with things like munitions, direct to supplier authority, playbooks for investing capital. For energetic materials, where building specialty capacity and hazardous materials handling is really as expensive, Predictable contracts and options are probably the single best way to make private capital and smaller firms invest at scale in safe manufacturing capacity. If the department follows through with this, I think it could become much easier to move from grams in the lab to kilograms in production. The third thing I see here is what's called mission engineering and industry engagement, MEIA. This new mission engineering construct exists to translate key operational problems, as they're called, these COPs, into clear, testable requests and to run experimentation campaigns with industry. That's a perfect vehicle for energetics. We can craft key operational problems that explicitly ask, show us a warhead fill that increases delivered pressure by X amount while meeting sensitivity Y and aging lifetime Z. And then you go and fund prototypes and experiments that prove or fail that claim quickly. That reduces the classic, quote unquote, it's interesting in the lab, but nobody asked for it problem. Fourth, I think technical and regulatory levers are being loosened. I think it's being done carefully, but they are being loosened. The reforms call for streamlining test and evaluation, for defined certification and qualification boundaries. Also, program acquisition executives can swap components within established safety and performance envelopes without restarting the whole system qualification itself. For energetics, that could mean a new formulation could be swapped into an existing warhead design if it fits predefined mechanical and sensitivity envelopes and things like that. Those kinds of changes could dramatically lower the cost and time to field. But those boundaries have to be conservative for explosives. Can't shortchange safety overly much. The last thing I'll mention along these lines is a reality check. None of this eliminates the hard constraints. You think about the environmental permitting for explosive production, ITAR and technology security and export rules, the long lead time for hazardous materials permitting. All of those, the reforms may reduce process friction and they create funding and prioritization, but translation of the potential they open up into production still requires explicit risk investment, expensive ones. And I think the bottom line is that these reforms, while creating the authorities, the money signals, the institutional funnels that could help to move new energetics out of the lab and into operational demonstrations and production, to capture those gains, we have to pair the material science up with mission engineering. We need to do all of these. We have to be ready to perform all of these linkages in that developmental chain faster and more efficiently. All right, let me close with this. Everything I've talked about today really collapses into one challenge, and that is more efficiently and effectively turning chemistry into capability. I think you can reduce it to 3 steps. Pair science with mission engineering, number 1. With the latest acquisition reform, we finally have mechanisms to link lab work to specific mission outcomes a lot faster than was true before. That means we can start running real experiments that ask, can this new propellant give us 10% more range, and while staying within insensitivity limits, instead of just, can we make it go boom? Step 2 is to invest in scale and safety. The defense energetics community knows how hard it is to build or modernize its facilities. All the things I touched on, the environmental permitting, the safety certifications, the need for skilled labor. That's exactly where investment counts. We won't regain industrial agility without physical plant and human capital. And finally, the third step, measure success by fielded capability. Papers and lab demos are great, but what moves the needle for warfighters are qualified, producible materials and real systems. That's how success should be defined, not through discovery, but through deployment. Put simply, the chemistry gives us the potential. The system gives that potential purpose. The reforms underway now, I think, give us rare alignment of science and policy and money. If we seize it wisely, we can close the gap between what we can make and what we can field. That's the path ahead. I think it's the path that'll decide who holds the advantage in the next war.
Thank you, Dr. Jones, for that presentation. We have a lot of questions that came in Is it okay if we go for a few more minutes with questions with you?
Yeah, that'll be fine.
Okay. Well,
I reserve the right to beg off answering a question.
that's fair. That's
Judge
fair.
myself to be technically competent to do so.
In your view, there's a lot here, and I'll summarize some of them, emerge some. What are the possibilities here, key challenges or possible breakthroughs to make use of a couple of the emerging technology areas, things like advanced manufacturing or advanced materials characterization, to improve the composition of new energetic materials or reduce manufacturing costs? So what do you think is most promising that we should be going after?
Which of those specific elements, or repeat the first
Yeah,
part of the
what
question?
specific elements are most promising as targets to improve? And then what emerging technologies do you think can help with those things?
That's a difficult question to break apart and answer, I think, fairly. Across the overall system, I would argue that the best and most targeted investments to be made on a system scale is in improving the resilience, depth, and efficiency of our manufacturing of energetic materials. If I had to prioritize one as against any of the other two or three factors in that developmental sequence, that's where I see the biggest vulnerability and the greatest degree of fragility. I also think it's essential for creating the downstream demand pull that will help to clarify and make more resilient the supply chains and the domestic supplier base for the precursors and other chemicals on which material production relies. That's where I would prioritize investments right now, if only because the immediate priority seems to be not looking out over a 5 or 10 or 20-year period, but in readying the overall ecosystem for what could be I don't want to call it apocalyptic or existential, but a very taxing conflict on the munitions industrial base. And I would argue that's the single weakest link in the overall ecosystem.
There's a question here about solvent-based propellants as opposed to solvent-less propellants.
I cannot address that kind of chemistry question. I'm sorry.
All right, we'll move on. Let's talk about workforce. So in this future where potentially we're making use of even CL20 or beyond, and we're growing our energetic materials industrial base, what do you see as the workforce challenges coming, and what are some of the universities and community colleges in the United States doing to help address that upcoming challenge?
Structurally, I think it's probably the most severe challenge that the energetics material enterprise faces, and that makes it similar to, if not identical to, every bleeding edge and legacy defense production enterprise across the department. We inhabit a mature, structurally very efficient labor market. The U.S. economy is extraordinarily good at assessing people's capabilities and fitness to do work, and we have probably the most efficient pathways in the world at allocating labor to its most productive outcomes. It's not perfect, but typical unemployment rates in this economy are 5, 6, maybe ruinously as high as 7%. You're competing for some of the very best labor in the economy in skilled terms, and it's not necessarily the sexiest domain in which to contemplate working, for the same reason that shipbuilding is facing such a severe labor problem right now. It doesn't pay tremendously well relative to the alternatives, and you're on the waterfront all day under terrible conditions. Working in a chemical plant or in a lab may pay reasonably well, but a really skilled and intelligent person has a lot of options. I think the issues associated with, number one, the aging out of the legacy labor force, both in terms of the highly educated, high-end scientists and engineers who occupy the apex of the development process, and the skilled technical workforce that makes possible and expeditious the development aspects of the ecosystem and the production. Replacing that is a challenge as the legacy workforce ages out. With the downturns in the early 90s, 90s and the early 2000s, generally speaking, in many of these operations, the first people let go were the youngest, and it created an artificially elevated age, so to speak. Finding the young talent to replace that retiring legacy workforce is priority number one. Number two, I think, is making the kinds of targeted investments in next generation materials in a new production ecosystem, the kind that new materials would imply is possible, and the kind that the acquisition reforms would seem to incentivize well, to predicate that on processes that are much more automated, much more labor efficient, much less dependent on consistent human input, especially in the automation and deployment of AI and machine learning in testing procedures on production lines, for example, things like that, all to economize the rarity and the high cost of that labor input. That's the most, I think that's the outlook on the labor question, the workforce question that I foresee is most pressing. The worst thing we can do is to continue incentivizing the perpetuation of and turning our back on the limitations of a workforce utilization process that resembles something from the second industrial age. I mean, I've visited energetics production facilities before, and what's striking to me is how good the people there are. They're really quite remarkable talent that our arsenals and labs still draw in, but they operate in facilities that are oftentimes little different from those their grandfathers would have recognized. And and the rest of the productive ecosystem in chemistry and elsewhere has moved on.
We have time for one more question. It's about the energetic material supply chain. To what degree is the supply chain dual use? So could precursors be used for other purposes? Could even some of the manufacturing capabilities be used for other purposes? And then therefore spread the cost and potentially support the industrial base. Is there overlap either in the commercial world or for their explosive uses, or even to completely different sectors in these supply chains?
I'll offer you a kind of impressionistic and secondhand response based on my interaction with production specialists in the field. And the answer is yes and no, and both, or half of each. The production process for energetic materials, the formulations that factor into munitions involve reliance on materials, lots of materials that have clear dual use potential, or actually are dual use and draw on the same producers and supply networks on which commercial producers of different kinds of things depend. And that's all to the good. I mean, that it helps to condition that market force, and the distributed character of that ecosystem helps to condition both the cost, the availability, the resilience of the materials in those networks. That's a huge advantage, but there are profound limitations to that. And particularly for the primary energetic materials themselves, the molecules, producing those tends to be highly specialized and very specific to defense purposes. They tend to be highly concentrated in single production units. Even in some of the smaller facilities that cater specifically to defense purposes, the cost of addressing specifically defense requirements involves a necessity to serve the civilian market as well at lower rates of capital return, because you're supporting a lower margin on your defense work. I can't tell you from whom I heard that, but it's very clear in the case of a very specific vendor of chemicals to the Department of Defense. This particular place has been in business for a long time and has a long history of dealing with the Defense Department. It's a very It's a stalwart American producer of patriotic materials for defense purposes. But the Defense Department has been a really finicky customer for 25 years. It's very difficult for them to make future capital allocative investment decisions about expanding plant or diversifying supply chains at different cost points in light of the lack of clarity about, where priorities will be in 2 or 3 or 5 years. And they can't build a line and shut it down and just move labor around in the facility and expect it to work when the time comes. So there is like in naval shipbuilding, which is the I think the parallel that makes the most sense given the scale and the defense specific character of a monopsistic market. You're dealing with an ecosystem that can benefit to some extent from dual use capability and the identity of materials and supply networks and processes with the civilian sector, the commercial sector. But there are really important determinative, decisive parts of it that are going to remain defense specific. And the country has to face, the hard, how much insurance risk are you willing to put up to ensure that that capability is there when you need it? That's a question squarely that people don't like to have to confront. Not when you're putting dollars against it that you could better spend in the near term on another priority.
That's great. Well, we're out of time, so I want to thank Dr. Jones for his great presentation and answers to the questions. Thank everyone for your attendance and your patience and the great questions you submitted. If you have feedback about this event, especially topics you'd like to see us cover in the future, please email us at eti@ndia.org. I also want to take this opportunity to highlight the next Tech 101. It's going to be on quantum technologies, and it's going to be done by Professor Paparao from New York Creates. That'll be December 2nd, 2025. Look out on NDIA's website's calendar of events for more information. To register for these and other ETI events, please visit www.ndia.org/events. Thanks again to Dr. Jones, and thanks everyone for joining us today.